pi is 0. So this kind of goes in the arc this way. Okay. All right, so cosine. Cosine just does the opposite. We just talked about cosine. So cosine of 0 is 1, so it starts up here. Cosine of pi over 2 is 0, so it goes down here. And then cosine of pi goes up to negative 1s, right? So it actually goes down here. So this looks like this. Okay. So the region we cared about, this is a little tricky, is actually right here. And, oh no, actually, sorry, right here is what we care about. So not this one, sorry, and this region here. So this is not correct right there. So it's this region here and this region. So this is S1 and this is S2 there. Okay. So this is talking about what we just talked about earlier. So we have to set up two integrals in order to do this. Okay. So we got to figure out, what's this point here, right? This is a sub 1 between 0 and pi, where they, actually cross each other. And that's pretty straightforward. All you got to figure out is when are they equal to each other. So in other words, when is sine of x equal to cosine of x, right? And that happens when x is equal to, I believe, pi over 4. Okay. So the area, as we set this up, is going to be the integral from 0 to pi over 4 of the top function. And so in this case, the top function is going to be cosine of x minus the bottom function, which is sine of x dx, plus the integral from pi over 4 to pi. And now this time, sine of x is on top, minus cosine of x on the bottom dx. And there we go. So we have to set up our two integration portions right there, which, isn't too bad to integrate anyway, since we know the opposite signs itself, right? So if we take the integral, again, integral cosine is positive sine. Integral of sine is, if you're not sure, just look at your cheat sheet. So integral of sine is negative cosine. So negative makes positive. This is evaluated at pi over 4 and 0, plus, again, just the opposite here. Integral of sine is negative cosine. Integral of cosine is positive sine, so it stays the same. Again, evaluate now from, pi over 4 to pi. Okay. All right, so we already know it's going to be equal to the same, right? That's in quadrant 1. So sine pi over 4 is radical 2 over 2. And it's going to be the same thing there, because they're just equal to each other. Okay. Minus, when cosine, so sine equals 0, that's just going to be 0. Cosine of 0 is going to be 1. That's the first part. Plus, and we do the same thing over here. So cosine of pi is negative 1. So that's just going to be positive 1 at this point. Sine of pi is going to be 0. So that's just 0 here. And then, so if you just want to do that, no, I just bring it in. So we plus, right, because it's negative. Over here, cosine of pi over 4, again, is just radical 2 over 2, and then minus radical 2 over 2. So notice this just cancels away, right? So all this goes away. So it's just a plus 1. Notice there's a minus 1, so that all cancels. So you just get this. So you get 2 radical 2 over 2, which ends up being a happy radical 2. All that work for just a simple number like that. Okay, so can you kind of notice it gets a little difficult as you go into it. Okay. All right. Last portion for this section is, well, I kind of said earlier, but I kind of didn't, is what if you don't have an upper or lower function to begin with? So you can't really define which is above and which is below. Okay, so in other words, they're up and down, not side to side itself. Okay, so for example, let's suppose we have a function looking like this and like that. So this is our g of x, and this is our f of x. Okay, and we want to find the area between, let's say, here. Well, we can't just do top minus bottom because these are just straight lines, right? This is going to be vertical lines. That doesn't really make sense. So what we do is we actually have to make our rectangle go in the opposite direction. So now we have to do it horizontally instead of vertically itself. So this is going to be our new rectangle going in. So it's not perpendicular to the x-axis. It's actually perpendicular to the y-axis. So now our bounds are essentially with respect to the y-axis. So this is from C to D itself. Now the cool thing is it follows the same template if I would just do this. If I flip it around, it still follows that portion there. So we're still going to take the integral, now from C to D. But the problem is now, again, it's respect to x. So it means you got to change everything with respect to x. So it's going to be x equals an equation. And again, easiest way to figure it, because remember if it was going to be, if you look at it this way, it is still top minus bottom. And the same thing applies, but now this time it's going to be right minus left. So when you take the integral with respect to the y-axis, it's going to be the top, so f of x, minus the left function, which is going to be g of x. So again, right minus left function to make it easier for you guys. Oh, sorry, dy. And this is, oops, sorry, these are respect to y, so these are y. So many x's everywhere, I keep forgetting which one we're at. Okay. So let's see an example so you can see what's actually happening if you do, going up and down, you don't have an actual one going across. And you'll see something that is actually easier instead of doing this whole process here, which is this example here. Okay, so find the area of the region bounded by the curves x equals y squared minus 4y and x equals 2y minus y squared. And notice they're already in that form. So you know we're going to be using this automatically, right? In other words, so we don't have to solve for x in general. But let's first just graph and see what's actually happening, right? So let's just graph this real quick and see what's going on. Now this you got to be careful of because we're doing the opposite direction, right? So now we're plugging in values for y and getting values out for x. Okay. All right, so we plug in 0 in for y, so we plug in 0 in for y, we get out 0 for x, which is nice, right? So get that value here. Okay, so if I plug in 1 in for y, so here, right, plug in 1 in for y, we get 1 minus 4, which is negative 3. So when y equals 1, x equals negative 3. When I plug in y equals 2, this is going to be 4, and this is going to be negative 8, so it's going to be negative 4. So when y equals, okay, remember, y equals 2, x equals going to be negative 4. Right? Did I get that right? Yeah. Okay. Yeah. And then if y equals 3, so y equals 3, that's going to be 3 squared is 9, and this is going to be negative 12. So 9 minus 12 is 3. So y equals 3, x is going to be negative 3. So notice it's coming back now. So it kind of looks like this. Yeah, like that. Yeah, it's probably going to go me the other way direction, yeah. Yeah. And then, so actually I could force it this way. It's going to be going this way here. Okay. So let's see what's happening here. So same thing, if y equals 0, you get 0 out, so it matches that point. If y equals 1, so if y equals 1, we get 2 minus 1 is 1, so when y equals 1, we get 1. So it kind of goes this way. If y equals 2, we get 4 minus 4 is 0. So 1, 2, 3, 4, we get 0. Oh, sorry, y equals 2. What am I talking about? If y equals 2, so it goes like this way. There we go. So it curves this way. If y equals 3, so this is going to be 6 minus 9, negative 3. Oh, so they cross at the same point. And they actually curve like this. If your y equals 4, you get the second value. So our curve is right here. And this is what we're bounding between. Now, if you're wondering what in the world, is remember, right? So to solve for which one we're going by is just set them equal to each other. We want to figure out those bounds. But you can kind of tell since we already have 2 points aligned itself, right? It's probably going to be from 0, 0, and 3. But just in case if you're not sure how to find the bounds of integration, just set them equal to each other. So you have y squared minus 4y